Okay, so let's determine if carbon tetrachloride is a polar or non-polar molecule given these two electronegativities. The electronegativity of carbon is 2.55 and the electronegativity of chlorine is 3.16. Now I'm going to bring up an important point here, but before we do that, carbon tetrachloride will look like this. Right, so carbon has 4 valence. Right, each chlorine is a halogen. You can notice that there's going to be 4 bonds here, so I'm just going to design the Lewis dot structure so you guys can see this. Okay, so it should look kind of like that. Okay, so you can see ample electron sharing, and in this case, if I draw out the structural diagram, you should see a structure that looks like this. So there is no lone pairs on carbon, and there's 4 bonding atoms. So there's 4 bonding atoms, 0 lone pairs. And the way I'm looking at this, I'm looking at lone pairs, bonding atoms, and the steric number, right? And if you guys don't understand this, go back and review the VSEPR videos. Anyways, so we have electron geometry of 4, and this actually is the hallmark feature of the tetrahedral geometry. And so the tetrahedral geometry, and it basically looks like this. Okay, so 2 bonds would be in the plane, and then 1 bond would come out of the plane, 1 bond goes into the plane, and the bond angle here is 109.5 degrees. Okay, so now that we understand this, right, you can imagine that all of these guys have valence electrons, but we're only focusing on the valence electrons on the central atom. And because they have 4 of the same bonds, we just have to test one of them. So I'm just going to test this bond here, right? We're just going to test this bond here. So if I'm testing this bond here, the electronegativity difference of carbon to chlorine is equal to the electronegativity of chlorine minus the electronegativity of carbon, which is basically 3.16 minus 2.55, and this gives us, what was this value? This gives us 0.61. Okay, so this tells us that this is asymmetrical electron distribution, right? Because we can understand that the electronegativity difference is greater or equal to 0.5 but less than 1.7. Okay, so as a result, a dipole moment is generated. Dipole moment generated. So we get this dipole moment generated, and it should point to the more electronegative species. So this is partial negative, and this here is partial positive. You can imagine that's going to happen here as well, right? So we can imagine that, and these bond lengths should be relatively the same. You should have one here as well. This is, we'll call this like mu2. We'll call this mu1 here, right? And if I look at this, you should also see a partial positive here, partial negative here, right, and so forth, right? So I'm just gonna kind of coordinate that. There should be another dipole moment created here, partial negative, and another dipole moment created here. Now the only issue here is that, well, we can notice that there aren't any poles being created, right? There's a positive on the inside, but on the outside there's complete negatives, right? So we have these 4 dipole moments. I'll call this mu1, mu2, in yellow mu3, and in orange mu4. Now you can label it any way you want accordingly, right? But you have these 4 dipole moments. We need to understand, okay, how is there a dipole being created, right? Is this in fact a polar molecule? Just because a molecule has polar bonds doesn't make it a polar molecule, right? And the best definition of a polar molecule exists as a dipole if the net dipole moment is not equal to 0. Okay, so what that means is the net dipole moment, if you add all of the vectors together, if you add all the dipole moments together, and this means sum of, this cannot equal 0. If the sum of all the dipole moments is equal to 0, then this is basically, there's no dipole created. Okay, so just because you have polar covalent bond doesn't make a molecule polar, right? So containing polar covalent bonds does not always imply a polar molecule. You actually need to follow these rules. So what do I mean by this rule, right? So as long as it's not equal to 0, right, it's polar. If it is equal to 0, this is nonpolar. This is a nonpolar molecule. Not a bond, but a molecule. It's the collective thing, right? So this is the polar molecule. So what does that mean? Well, when we're adding these dipole moments, these dipole moments are vectors. So a vector quantity has the direction and the magnitude, right? So I'm going to redraw that in the next page here. So let's take a look at this molecule again. And if I want to find the dipole moment here, the net dipole moment, which is the sum of all the dipole moments, I'm going to add mu1 plus mu2 plus mu3 plus mu4. And you can imagine here that these are vector quantities, right? So if you've ever taken physics courses, we would represent it with an arrow on top, right? I'm going to just show you how to do vector addition. If you do vector addition, guys, you're going to add the vectors tail to tip, tip to tail. Now this is your dipole moment, right? This is the tail, and then this is the tip, and you start with one of the dipole moments. Let's do it in the order of how I wrote it out. Let's start with mu1. So mu1 I color coded in blue, and how I'm going to add the vectors, I'm going to draw them out. I'm just going to copy and paste. So it's like me copying this and moving it here. So this is mu1, right? And then I'm going to add this with mu2. So mu2, you're going to add the tip of mu1 to mu2. So mu2 kind of looks like that. Okay. And if you really wanted to be accurate with this addition, you would actually have to measure them out appropriately and basically add them tip to tail, tail to tip. But we'll just kind of sketch it out, right? So that's mu2, and then I'm going to add mu3 here. Okay, so mu3 it kind of looks like this. Whoops, let's just do it here. Okay, so this is mu3, right? So that's mu3 here. I just copied and pasted it there. And I'm going to add mu4, right? And if I actually measured this, you could actually see that it should have added to the correct spot. I just kind of... So this is one of the issues. You got to actually kind of measure it. So this is kind of what it should look like. But you guys can get the idea, right? And this is mu4. And this is where we started. So we actually started at this point here. This is the initial point, but you can see that when we added up to mu4, we also ended up, our final spot was our initial spot. So this means the vector addition is 0. If it creates a polygon, any kind of shape, a closed figure, it adds up to 0. That means that where we ended up is where we started. So this tells us that this is not a polar molecule, not a polar molecule. Okay, I think recently we also checked out these two molecules. We looked at formaldehyde and we looked at water, and I drew out these dipole moments. So the dipole moment here was just towards the oxygen. This is partial negative, partial positive, right? And we also looked at these dipole moments. The dipole moments here were going this way for water, right? You want to put the valence electrons here as well, but right? So as a result, then you get a partial negative here, partial positive here, right? And this methodology works for some of the molecules, but this actually works for all of the molecules. And you can see here that the net dipole moment for formaldehyde, if this is mu1, it's just equal to mu1, and that means that you can see that this is not 0, because this is where you started, this is your initial spot, this is your final spot, it's not equal to 0, right? So this is a polar molecule. Let's take a look at water. If you're looking at water, I'm going to call this mu1, mu2, right? If I add up the dipole moments of water here, if I want to find the net dipole moment, right? You can call this the net dipole moment if you guys want, right? Basically a mu1 plus mu2, right? So you're adding mu1, which looks like that, to mu2, which looks like that. Whoops, let's just move this out here so you can see it better. This is mu1, and then this is mu2, and this is where you started, but this is where you ended off. So this is not a polygon. It doesn't equal 0. So this also tells us that this is a polar molecule. So this methodology where you add up the vectors, if you add up all the vectors, right? If you find that, and this is how we're going to summarize this, but if you find that the sum of the dipole moments is equal to 0, this is a non-polar molecule. And if the sum of the dipole moments is not equal to 0, this is a polar molecule. Or you can think about the net dipole moment as the sum of the dipole moments, and this in fact is a vector quantity. So this is the idea that we want to kind of put out there, and this is the method that we're going to be using to determine if molecules